Okay, so as I mentioned, today we're going to lay some foundation for all the things that we're going to be talking about in this class, all right? And again, just so you understand what I'm trying to do here, and maybe you've never had a math class like this before, but my goal is to take what we're going to be talking about and anchor it into a bigger context. Because I think if you see it in a bigger context and how it relates to each other and how it relates historically to all of mathematics, I think that not only will you have a better appreciation of it, but you'll maybe understand it better and be able to process it better, because math really isn't just here's a skill, do it, here's a skill, do it, here's a skill, do it. That's not really math. That's not what math is. That's like just skills, okay? And I heard a great quote the other day. It was, we study math for three reasons. We study math for calculation, we study math for application, and then we study math for inspiration. And that's the part I think is missing so often. Now, today's lesson may not be all that inspiring because we're going to take a grip of notes, but at the same time, if we start to see math in the bigger picture, then that's when we can actually appreciate it and maybe even be inspired by it. Okay, so some of this stuff I've shared with you already, but we're going to go ahead and put it down here in some note form so that you have it to work with. So Euclid's Elements was written around 300 BC in Alexandria, Egypt. Which was kind of a learning hub at the time. It was a new city, and the Greek thinkers had all sort of flocked together to kind of hang out there. It was like the hip, cool place to hang out. So Euclid's Elements is one of the most influential works in the history of mathematics. One of the most influential works in the history of mathematics. So the Elements itself is a collection of 13 books. They lay the foundation of geometry, number theory, and logical reasoning. And again, we'll talk a little bit more about this as we get further down into our notes, but really this was the whole idea of the change in mathematical thinking with the Greeks and the Romans was, well, really more the Greeks and the Romans. The Greeks, they were all about logical reasoning, and they were all about proving things to be true. And that's what Euclid did. That was what was the beauty of this was the first time that some geometry things that had always just sort of been accepted were actually proved to be true. So the stuff that's in Euclid's Elements, not all of it was, like his invention. Things have been used, and we'll talk a little bit about that too. But it was how he could show that these things are definitively true in a logical pathway. That was what was so beautiful about it. So I give you this little visual, kind of the breakdown of the 13 books. So the first 4 books focus on something called planar, Planar, planar geometry. We'll talk about planes a little bit, but essentially that's a flat surface. So flat surface geometry. Then we got books 5 and 6 dealt with ratios and proportions. Then books 7, 8, and 9 were centered around number theory. Book 10 dealt with irrational numbers. These are your decimals that don't repeat and don't terminate, irrational numbers, your square roots of non-perfect squares like the square root of 2 or the number pi or phi, those numbers. And then the last 3 books, 11 through 13, focused on solid geometry. And when we say solid geometry, what we mean is 3-dimensional geometry. So 3D geometry. 3D geometry with 2D flat surfaces, though. And we'll talk a little bit about how that changed with non-Euclidean geometry later on down the road. Okay, so just kind of some notes on how this kind of came about and the historical significance of it. So what Elements did was it introduced a logical, step-by-step way of proving mathematical ideas using simple starting assumptions called axioms. AXIOMS, axioms. These were simple starting assumptions, and he built off of those. This set of books served as the world's main geometry textbook for over 2,000 years. And I shared this with you guys. It is also the second most printed book in all of history, with the Bible, of course, being the first. Now, there are some famous results in here, like, for example, the proof of the Pythagorean theorem. Most of you guys should know what this is. Pythagorean theorem. Theorem is Theorem. That's a word you'll become familiar with. A theorem is an idea or a concept to be proved. Again, we'll talk about that in a little bit. Another one was the proof of infinitely many prime numbers. These are some of the big dogs that came out of some of the early work in elements. But really, there was so much more to it in just the way that it put it together. And then lastly, it ends with a study of the 5 perfect Platonic solids. So we're going to take a few minutes just to talk about these because they're kind of interesting. So these are the only 3D shapes that can be made possible, that are possible to make, where each face is the same regular polygon. Okay, well, we just did a construction. We talked about a regular hexagon and a regular octagon and a regular dodecagon, right? And one of the highlights of a regular polygon, I told you, was that all of the side lanes are the same, right? And so if you take these regular polygons and you assemble them together, these are the only 5 3-dimensional solids that you can make where every face is a regular polygon. And Euclid proved that. Now, this was known previously. We'll talk about that in just a second, but these were known about, but Euclid proved in his solid geometry section that these were the only ones that you could make, and he showed why that is. That's kind of an impressive feat. So I wanted to just point these out to you because we're not going to probably get to these in our class, and so I wanted you to at least be familiar with them. So this 4-faced equilateral triangle one is called a tetrahedron. Tetrahedron, Hedron. These are all going to end in hedron. So these are 4 equilateral triangles, and at each corner, you've got 3 triangles that meet. So the backside is a triangle and the bottom is a triangle. And so for each corner, no matter where you pick a vertex, you have 3 equilateral triangles meeting at that corner. Okay? Then we have a hexahedron. Sometimes we call this a cube. This had 6 faces, and what you end up finding is that you have, pick a corner, any corner, it doesn't matter which one you pick, and there's always 3 perfect squares that meet at that corner. So when you assemble them together, there's always 3 perfect squares that meet. All right, this one is called a octahedron. This has 8 faces, again, equilateral triangles. There is no middle piece to this. It's just, as you pick a corner, you will find that there are 4 triangles that meet at that corner. Like, for example, I'll just pick this corner right here. Look, there's 1, and then this side 2, and then here 3, and then 4. So there's 4 triangles that meet at every single corner. All right? This one is called a dodecahedron. Hey, we did a dodecagon the other day. Dodecahedron. And this is made of 12 regular pentagons. Okay, so these are our 5-sided shapes, right? And so at each one of those, there's 3 pentagons that meet. So like, just look at this corner right here that I highlight. Can you see the 3 pentagons that meet at that corner, right? Okay. And then the last one is called an icosahedron. An icosahedron. This one is a 20-faced shape. Again, all equilateral triangles. 5 triangles meeting in a corner here. I'm going to pick a corner right here. Look up on the screen. Can you find the 5 triangles that meet there? You see them? Okay. And these are the only 5 shapes where you can take a regular polygon and assemble them together and make 3D solids. Okay. And again, that's what Euclid proved in this. I don't know if anybody here has ever played any role-playing games with dice, but I grew up playing Dungeons and Dragons. These are the Dungeons and Dragons dice right here. They're all that. There's a 20-sided die. Roll a 20-sided die to determine what your character does. Roll the 12-sided die to get this response. Like that was actually shaped after the Platonic solids. You can still find them on Amazon. You'd be like, hey, let me see Dungeons and Dragons dice. Look them up, and you'll see that there are 5 dice that come in the set, and they are all the Platonic solids. So it's kind of an interesting little side fact for you. All right, so what I want to do now is I want to talk to you guys a little bit about the history of mathematics. Because, like I said, everything comes into a big package, all right? And so I want you to see some kind of interesting things, hopefully, about the history of mathematics. And so I have a little timeline here for you. I'm going to hit some high points, but let's just take some notes. So the first one I'm going to call ancient civilizations. Ancient civilizations. And this is running approximately 2000 BC to about 600. We'll go with 600 BC. Okay, so this is Old Testament time right here. This is, when the Old Testament was happening. By the way, if you've never taken a look at my little poster on the back, you should look at it sometime. It's kind of interesting. It's the biblical and historical combinations of things. And then at some point, my goal was always to go back and put math in there as well on little flags. It's something that I want to do, but haven't really gotten around to that yet. But that's something to do. So anyway, in the ancient world, math was very practical. Okay, so it was used for building and astronomy and measuring things. And there are stuff that are attributed to later mathematicians. Like you can see here, the Babylonians used what we call Pythagorean triples. Okay, but Pythagoras wasn't a person when the Babylonians were around. But it's attributed to him, but they knew about it. That's the thing. And so there are math concepts that have been used for thousands of years, but then they became more formalized as history went on. The Egyptians, fractions. One of the things that's fantastic about some of the old Egyptian math is the way that they used fractions in engineering to build the pyramids. That's how they actually did math to come up with the way that they could build the pyramids. So ancient math was very practical. That was it. It was about, we're going to do stuff with this, okay? And then we move forward into the Greek and Roman era. Sometimes it's called the Greco-Roman era. So this is the Greek and Roman era. Okay, so this is about 600 BC to about 500 AD. Okay, this is New Testament time, right? Jesus comes in here. Saul we're talking about, right? We're talking about all these things happening in the New Testament. This is the New Testament time. And here's where the big change in math comes. Up to this point, math was very practical. And then the Greeks come in, and the Greeks are philosophers. You guys have heard of Plato, Socrates, Aristotle. Some of those names sound familiar, right? These were known as the great thinkers of the time. Okay. And so they came in, and math now became this philosophical thinking science. In fact, let's talk about Plato for a second. Take a look at the name of the solids, the Platonic solids. Hey, boys, can you focus it in? Thanks, because you're distracting me, okay? And I don't want to be distracted. So the Platonic solids were actually brought into the world through Plato, and he used these to represent different things in his philosophy. So, for example, the tetrahedron was how Plato represented fire. These are the building blocks of the universe in Plato's world. And so he used a hexahedron as a representation of earth. He used an octahedron as a representation of air, a dodecahedron as a representation of water, and an icosahedron as a representation of the cosmos. And so from a philosophical perspective, this is what Plato did with these solids, and that's how they became famous, right? And he said, well, these are the 5 solids that describe all of life and all of creation. And then Euclid came along and said, let me show you mathematically how you can only make these 5. And then people went, wow, that's amazing. Okay, so Plato was kind of interesting in that sense, right? And so then we see some of these big names, right? Here he is right here, Pythagoras, right? Again, he was not the first guy to figure out this measuring relationship, but yet he was the first with his school of believers to kind of popularize it. Of course, we're talking about Euclid. I mentioned Archimedes the other day, right? So Archimedes, he estimated pi using the hexagon, octagon, dodecagon, and then just kind of getting closer and closer to a circle. Archimedes is famous for a lot of different things. He was known for levers and buoyancy. He figured out how to move water up a hill using an auger. We still use this technology today. Like if you drive to LA, you go over the grapevine, you see these big pipes going over the grapevine and how they get water up. There's like these augers inside. And then it pushes the water up the hill. That was Archimedes' design. You could actually look that up on the internet and see how things that were, 2,000 plus years ago, we're still using today. Okay. Then the Romans sort of, they were like, okay, well, that's great. You guys can think about math, and you can talk about it, but we want to use it. So the Romans were much more practical. Like if you've ever heard of the Roman road. Okay. So the Roman road was an engineering wonder at the time. It was a wonder of the world. Okay. And it was just like amazing how they could build these roads, but that was an engineering thing that they did with mathematics. Ptolemy is interesting. So this Roman thinker, he actually invented something called trigonometry tables. Well, he didn't invent it, he discovered it, trigonometry tables. You're going to use those this year. You're going to use trigonometry tables. You're going to see what they are. And so then you'll be like, oh, look at that. Now I'm using math from, again, the Roman era. Okay. So there was a lot going on at this time. But again, this whole idea with the Greek thinking was they wanted to prove things. Like, okay, if you know anything about that Greek time, if you've heard, did you guys take you taking world history? You're in it right now? Or you took it? Like one of the big things was orators, right? And so like one of the things that they loved to do in the Greek culture was argue. Right? That's where debate comes from, right? One person would stand up over here and he would say, blah, 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 blah. And this person would over here go say, really? Prove it. And then this one would say this. And then he would go, well, I don't think so. And this guy would say, really? Prove it. And that was their whole culture. It was, you're going to say something? Great. Prove it. You're going to say something? Prove it. And that's what Euclid did. He was like, okay, well, we're going to say these things about math. Okay, prove it. I will. And he wrote it down. And he made 13 books out of it in a logical order. First one to ever do that. So that's what's so unique about this was because it was never done like that before. It was always about, hey, how can I just use it to, get my sheep in line or make sure my, crops are all lined up. And he's like, from this philosophical idea, he's like, I can show you that, while this is what Plato says the cosmos is made of, I can show you that there's no possible way to make anything other than those 5 shapes. Well, that's kind of interesting. So, okay, so let's keep rolling here. So, historically, what happens is the Roman Empire spreads, kind of takes over Europe and, Turkey and Iran and Iraq and, Istanbul and all of that is all over there, Constantinople, right? And then they start getting sacked by all the Germans and the barbarians and come in. And so the Western Roman Empire falls, the fall of Rome, okay? And so basically Europe goes into what we call the Dark Ages, right? They lose their libraries and their learning and they just kind of just wander around like, hey, we just been whooped up by all of these uneducated people. Now we're all just sort of uneducated. But the eastern side of things, all right, out in Istanbul, they kept things like they kept all of the thinking math and they kept preserving the books and they were continuing to study and move forward. And so we see this kind of, juxtaposition of going on of the Dark Ages, while at the same time, sort of in the Eastern Roman Empire, they're progressing with their thinking. Okay, so we call this the early, middle, and Dark Ages. So I'm going to put early, middle, or Dark Ages. And the dark part refers to the Western Roman Empire. So this is about 500 AD to about 1000 AD. This is going on. Now, there's some interesting things that do come out of this area. Like, I want to point out this guy right here. Al-Khwarizmi. I always have a hard time saying this guy's name. Al-Khwarizmi. Okay. So he was an Islamic mathematician, and he wrote a book called Al-Jabr. Algebra. So first place that algebra shows up as a title. It came from his book, Al-Jabr. And then Al-Hazan, this guy right here, he was known for applying geometry to lenses and spheres. Glasses. This is where things start to develop out of there. So there were some interesting things happening in the thinking part of the Eastern Roman Empire. Well, okay, so the Western, they're kind of just lost for a while there, but then they start to kind of come back around. And so we're going to call this the High Middle Ages. Or sometimes this is known as the Renaissance. Anybody ever been to a Renaissance fair? Yeah? What goes on at a Renaissance fair? Right? And what's everybody dressed up like? Funny hats, right? And there's knights and shining armor, and there's sword fights and jousting, and right, that's this time in history, right? This is King Arthur and the Round Table and all of that. That's what we're looking at in the Renaissance time, right? And so here's what happens. This is the Western Roman Empire starting to catch back up again. And so one of the ways that they caught back up again was that Elements became the most popular textbook of the time. And so the people who were rising up and now becoming the educated ones were saying, hey, listen, if you want to join our smart people group, you need to be studying Euclid's Elements. And so it makes a kind of a rebound in here. So I wanted to talk about this guy right here. So in the history of mathematics, Fibonacci, he is famous for bringing the Arabic numerals to Western Rome, and that's why we use numbers like 1, 2, 3, 4, 5, 6, and we don't use IV anymore. So that's actually the change that occurred and why we use those numbers now. He also discovered a very amazing sequence here. Let's write it down just real quick. It's really impressive. The sequence of numbers goes like this. It's 1, 1, and then 2, and then 3, and then 5, 8, 13, and so on. Anybody know what the next number is? What's that? Why 21? Yeah, 13 plus 8 is 21. 8 plus 5 is 13. 3 plus 5 is 8. 2 plus 3 is 5. 1 plus 1 is 2, right? And so the Fibonacci sequence actually is this idea of the next number in the series comes from adding the two previous numbers to it, right? This is deep. This is very deep. Yeah, in fact, this goes to something called the geometric spiral. I actually put it on your notes. It's like right back here if you want to look at your notes. This is a picture of what's called the Fibonacci spiral or the geometric spiral. And it has to do with the areas of squares and the way it's all assembled together. I've been kind of geeking out on this lately. I'll show you. This is what I do in my free time. You're like, Farkas, you are so weird. But I took my compass and I actually constructed it on the 0.5 centimeter graph paper. And so I went a 1 by 1 square, and then I added a 2 square, which makes a square with a side length of 3, and then that 3 square lines up with a side length of 5 and 8 and 13 and 21, and so it creates this spiral. And I was using my compass to build around there. So yeah, I'm a dork. It's all right. I'm comfortable with myself. So anyway, all right, here we go. Moving on. Anyway, so Fibonacci, very famous mathematician of the High Middle Ages. Okay, so let's get into the early modern. We'll jot this down real quick. Early modern time. This is sometimes also known as the Enlightenment period. I mentioned this to you guys when I was just kind of giving you a little brief introduction to this class. So this is about 1600 AD to 1800 AD. And just some of the big names that kind of jump out here that I've mentioned to you before. René Descartes. Right, this is our coordinate geometry guy, XY planes. This is where math becomes more symbolic and algebraic in terms of its popularity. Not the first time we've seen it, right? Algebra, but still, this is where it becomes more popularized, and then we begin to do this algebraic or analytic geometry that I mentioned to you. That's where this comes out. Kind of another interesting that happened in this time. I keep forgetting this guy's name. So it was Isaac Newton along with Leibniz. So Isaac Newton and Gottfried Leibniz. These are two mathematicians. You've heard of Isaac Newton, right? The apple fall on his head, right? Okay, but that's not really his thing, okay? Like, that's not the big thing. The two of these guys were studying mathematicians, and they both came up with the concepts of calculus totally independent of each other. Like, that's kind of crazy if you think about that. Like, they both came up with the concepts of calculus totally independent of each other. They weren't talking to each other at all, but it was because they were studying the same historical mathematics, they came up with the same result. That says something about the line of mathematics and how it rolls in connection. So, and then there's this guy right here, Leonhard Euler. I know it looks like Euler, but it's Euler. It's pronounced Euler. maybe the most influential mathematician in all of history. This guy, there are buttons on your calculator because of this guy. The pi symbol. This guy basically made the pi symbol and associated it with the ratio that was understood previously. Imaginary numbers. If you look at your calculator, you'll see a little e to the x. That e is Euler's number. And you guys are actually going to do some Euler construction work in this class as well. So he's also famous for another problem called the 7 bridges. And it's this idea of, can you walk across 7 bridges? Königsberg is this town. It's like, can you walk across these 7 bridges without walking back over one of them? And it was this pattern, like a puzzle to try to figure out. And he had actually figured this out. So it's a very famous guy, very influential mathematician. Okay, and now we get into, lastly, the modern era here. Which is about 1800 AD to the present time. And math at this point becomes abstract. It also becomes applied to specific fields. We see Carl Gauss comes up with non-Euclidean geometry. I kind of mentioned that earlier. So Euclidean geometry is what we call planar geometry, flat surface geometry. So non-Euclidean is non-flat surface. It's geometry on a curve. Think about like if you had to do geometry on the sphere of the Earth. That's what non-Euclidean geometry is. A lot of other popular mathematicians in this time. This guy, Alan Turing, he is famous for a machine that he invented that broke the German code that was telling the German submarines where to go to sink the boats that were supplying Britain in World War II. And because they were able to avoid these boats, Britain was able to stay supplied, and World War II was said to have ended years earlier than it may have because of the fact that they were able to circumvent the secret transmissions that the Germans were sending, all because of this machine that this guy invented. And that machine essentially became the foundation for all modern computing. So, I mean, computers come from that guy right there. So, kind of just an interesting thing. So, anyway, historical stuff. Again, math is just, it's God's design, you know, and it's just us finding it and then appreciating it. So, anyway, all right, so there you go, a little history of mathematics. All right, let's get in the foundations of our class. So this is what Euclid did specifically. We're going to focus on book 1 because that's where we're going to spend a lot of our time, okay? And so this is what he did specifically to build his foundation. He built it on 3 things that are called definitions, postulates, and common notions. Definitions, postulates, and common notions. Okay, so essentially definitions were accepted geometrical concepts already considered known at the time. Okay, we can all agree that this stuff is geometrical stuff. Okay, great. Yeah, we've seen it used before. The Babylonians used this. The Egyptians used this. Yeah, we've even talked about these things. We can agree that this is accepted common knowledge. That's what the definitions are. Okay. Now the postulates are accepted geometrical skills or physical things that we can confirm, that we can say, yeah, these are definitely things we can all agree on that we can do. And then lastly, the common notions were just accepted mathematical concepts, not specifically to geometry, but just like we could say, you know, when it comes to math in 300 BC, we all agree these things, it's common knowledge. And it was from those pieces of common knowledge that he began to build out his definitions, and then he began to build out the rest of his study. All right, so let's kind of cruise through this section. So upon these 3 building blocks, Euclid assembled his study of mathematics, which was consisting of proofs, like I talked about. He's proving things. And his proofs are historically called propositions. His proofs are historically called propositions. If you look up Euclid's Elements, the first words you're going to see pop up on any search: definitions, postulates, common notions, and then his propositions. And we actually, when we did the equilateral triangle the other day, I told you, you guys just did Euclid's first proposition. The very first proof that he does, we just did in class the other day. Now, these proofs were structured in a logical order with later proofs using concepts and relationships developed from previous proofs. And so structured so that the later proofs built off of the previous proofs. In book 1, Euclid has 48 propositions. There's 48 of them in book 1. And these can be categorized into 2 groups. There are problems, and then there are theorems. And essentially, problems are things to do, namely constructions, like what we just did in class. And then theorems are concepts to verify. So it's kind of like, do this, then do this, then do this. Now let's take some of those and think about how do they relate to each other, and let's say this. Proposition, or problem, and then put those problems together, and now we can verify a theorem, and then we'll use another theorem, and maybe that will allow us to build another problem, and that's how it goes down the line. All right, now each proposition, as I mentioned, whether it's a problem or a theorem, uses the previous propositions and or definitions, postulates, and common notions. Again, I want to reinforce this language with you guys. That's why I'm having you write it in at the time. So again, think about like the equilateral triangle. If that's his first proposition, then that means the only thing he could have used were definitions, postulates, and common notions, and we'll see that as we continue to talk more about these things. All right, so this, again, Elements was written in the Greek tradition, which was logical proof verifies truth. Things aren't true until they're proved. That was the Greek mathematical tradition. Okay. Now, book 1 is an impressive march, starting with the most basic accepted mathematical truths, things we can all say in 300 BC. These are common knowledge. And he ends with the most famous geometrical result of the time, the Pythagorean theorem. Okay, so we mentioned this previously that it's contained. This is the of book 1. That's what this is. In fact, propositions 47 and 48 are the constructing of to prove using the other previous constructions and theorems, the Pythagorean theorem. And there are hundreds and hundreds of Pythagorean theorem proofs now. There's all these different Pythagorean theorem proofs, but Euclid was the first one to do it. But book 1 is so much more than just a march towards the Pythagorean theorem. It systematically introduces and establishes a lot of what we're going to study today in, again, what we call planar geometry. Things like triangle congruence. This is a big one. We're going to talk about how can I prove that 2 triangles are absolutely 100% exactly the same. Or angle theorems. We'll look at ways to prove that certain angle relationships exist. And parallelograms are a big one in planar geometry. And these are all things that are a common part of every high school geometry class. You go to high school geometry class at Clovis North, you're going to see triangle proofs and angle theorems and parallelogram properties and all this stuff that comes from book 1. But the benefit for you guys is you get a little historical background and where it's situated and how it goes. And then hopefully we can sort of develop it in a logical pathway. All right. So for the last part of our class here, what I want to do is I want to establish for you what are the common notions, what are the propositions or the postulates, and then we will start working our way through the first definition so that we have that information to begin talking further about what we need to do in this class. All right, so let's start with the common notions. There are 5 of them. I'm going to give you the old school language, the translated language of these, and then we'll kind of put it into our own terms, all right? So like, for example, the first thing in 300 BC that everybody would say, yeah, we can all agree upon that, is that things which are equal to the same thing are equal to each other. Things which are equal to the same thing are equal to each other. Maybe you've seen it written like this. If A equals B and C equals B, then A equals C. Seen that before? Does that sound familiar? You should have seen it before. You've seen all these before in Algebra 1. This has a special math name. Anybody know what it is? Begins with a T. It's a property of math. What? No? Good try. We are going to do that this year. This is the transitive property. Transitive property of math. You're like, that's a hot minute since I heard this language, Ms. Vargas. Yeah, that's true. Okay, how about this one? If equals are added to equals, then the wholes are equal. If equals are added to equals, then the wholes are equal. But you just did that. You guys were just doing this, weren't you? What's this called? This is also a property of math. Whatever you do on one side, you got to do on the other side with addition, right? It's called the addition property of equality. And when we reverse that process, we end up solving equations. It's the addition property of equality. So yeah, the algebra that you were just doing at the beginning of the school year. Yeah, that's like, pre-Christ algebra. Sure, okay. If equals are subtracted from equals, then the remainders are equals, right? So if we have some equal values and we take away the same amount, does it matter if we're talking about numerical numbers or if we're talking about, gold coins on a scale? We take the same amount from both sides, they remain equal. What do you think this one's called? Yeah, it's the subtraction property of equality. Very good. So stuff that we still teach in our math class is actually rooted right here in the common notions of Euclid. Okay, this was another one. Things which coincide with one another are equal to one another. Okay, so I'm going to, if you want to, like with your straight edges you can or whatever, I'm going to draw a little triangle here like this. Just use my digital tools. And then I'm going to take my little triangle and I'm going to make a copy of it. So you can draw a second one. And I think I'm going to change the color of that one just to make it look a little different. Okay, so here's the idea of things coinciding with each other. If I can take this purple triangle and I can move it so that it sits directly on top of the black triangle, and those things line up perfectly, they coincide with one another, then I can say that those two figures are equal. That's a geometrical way of showing this. There's also a numerical way of showing it. Like, let's say I gave you 12 is equal to 12. Something is the same thing as itself. That's also a math property. Do you know what that one's called? All right, thanks. And then we can catch you up and just at the end I'll talk to you about what we did. Anybody remember what this one's called? No. It begins with an I. It's like looking in the mirror. It's your because they're equal. It's your identity. It's the identity property of mathematics. This stuff's starting to come back a little bit now. You're like, oh, I remember hearing all that. This is the identity property. Sometimes when we look at it from a geometric position, you could say it's also called the superposition property, right? Because again, Euclid did this comparison with figures and not values. We can do it with both now. And then lastly, there's the whole is greater than the part. And so I'm going to draw myself a little circle. You can draw yourself a circle too. I'm going to break my circle up into some pieces. I want that one. So I'm going to go like this and like this. So you can kind of draw the same sort of thing. I'm going to do two of them so that I can compare them to each other. And then I'm going to grab my highlighter. I'm going to do a little coloring here. I'm just going to color in my whole circle over here on the left. And then, of course, over here, I'm going to color in this. And then that allows me to make this statement that the whole is greater than the part. Again, I'm doing it with figures. But I'm saying the same thing as if I said this. Right, we would all agree with that number statement, right? But again, Euclid was doing this with figures, and so he would take this whole circle and then this part of the circle, and then he would say, okay, according to this, the whole is obviously more than the part. And so this is called the whole part relationship. So these were the things that people accepted to be true at the time that Euclid was writing Elements. These are general math concepts that everybody said, okay, we can all agree upon that. That's good. We got that. We can all agree upon this. Then he said, okay, well, let's talk about geometry. What can we all agree upon about geometry? And one of the things that he said that we can all agree upon about geometry is that we can draw a straight line in between any 2 points in space. So if I took this pathway here and I had some point in space and some point in space, I could draw a straight line between that. It wouldn't matter where that was. If I had a point here and I had a point here like that, I could take and I could draw a straight line through any 2 points in space. Put them on a paper, you could draw a straight line through them. Everybody said, okay, we agree with that. We can do that. That's good. You can use that as an already accepted rule. He also said we could produce a finite straight line continuously in a straight line or in another straight line. So like, for example, we could have a line that looks like this. And then I'm just going to change my color here just to make it a little bit different. And what I could do is I could take that line and then I could extend that line out as far as I wanted. So basically I could take any line piece, any straight path that I had, and I could extend it in either direction as much as I needed to do whatever it is that I needed to do for my problem, my construction. Okay? So that was one thing that he said. He also said that we could all describe a circle. We could draw a circle with a center and a radius of any size at all. And so he would give us something like this. He would say, okay, well, you could have a small circle like this. And of course, circles have centers, and we'll talk all about this in more detail. And then we have these radiuses measurements. We did this the other day, right? He says you could do that one. Doesn't really matter how you do it. You can do them of any size as long as it's got this, what we call this center point, and it's got some line measurement radius like that coming down. Kind of like how we started our first construction. So you can draw a circle, which we did, right? So we kind of used his postulate there. We were like, all right, we can do this. We have this tool that allows us to draw a circle. So as an accepted practice, we can do this. Another thing that was accepted was that all right angles are equal to each other. So maybe we have a straight line coming down like this, and then another one going across like this, and then we have this indication on that relationship. And again, we'll get into more details of this. Whether we draw it like that, or let's say we draw it like this. A right angle is a right angle is a right angle in any way that we put it, even if we spin it and rotate it and flip it and whatever. And everybody said, okay, we agree with that. That sounds good. We know what you mean by that. And then this last one's a little weird. Like listen to how it reads. That if a straight line falling on 2 straight lines makes the interior angles on the same side less than 2 right angles, then the 2 lines extended indefinitely will meet on the side on which the angles are less than the 2 right angles. Say what? Okay, I'm going to show you how this one works. Don't draw it yet. I'll tell you when you can draw it, but let me give you the idea how this one works, okay? It's kind of like this. Let's say we started with a straight line and a straight line, and then we had another straight line fall on those 2 straight lines. That's the idea, okay? And let's say that it fell in such a way that we had these 2 right angles. And because of the previous postulate, we know that all right angles are the same, okay? And so then what he's saying is, well, let's say that line fell in such a way that these angles that were once right angles are now smaller than right angles. He's saying, well, if that's the case, what's going to happen is because we can extend any line indefinitely, right, from the second postulate or third postulate up above, right? So he's saying if we extended those lines indefinitely, what would eventually happen is they would cross. If the interior, this will become an important word for you, the interior angles are both smaller than 90-degree angles. That's what that's trying to say. That's the picture you should draw for that one. Okay? Does that make sense now? It's a little bit easier once you see it explained like that, huh? Common notions and postulates. The things we can all agree upon that we could say, we agree upon this mathematically, we agree upon this geometrically. Here we go. We're good. Good place to start. Okay, so then from there, Euclid starts breaking into his definitions. And again, I'm going to give you the old school language of the definition, and then we'll explain it out. So the very first definition, the very first place he starts, and by the way, if you look at any modern geometry textbook, they're going to tell you that the very first thing you talk about is point, line, plane. It's the first thing you talk about, right? And here it is right here. The reason why is because we have to talk about a point. And so a point is that which has no part. Okay, what does that mean? Well, a point is a location in space it is considered no dimensional. In other words, it has no length or width. In fact, for that matter, it really isn't even a thing. It's just right there above Evan's head. No, wait, no, it's over here. It's above Ginger's head. No, wait, it's right there on the desk. It's over there. It's just a location in space. However, we have to be able to talk about it, right? Because it has no length or width. It cannot be measured. So then how do we talk about it? How do we indicate it other than just, hey, over there, and be more specific? So it's notated in this way. We always use a capital letter to notate a point. And that's usually either at an intersection, or sometimes we'll put down here end of a segment. We'll get into that in just a second. Or if it's just out in space, we use a dot. So for example, this is you're going to draw these in over here. So maybe we have something that looks like this. And then on that diagram, we could put an A here at this intersection of these two straight paths, or we could put a B here at this end, or a C here at that end. And now we can talk specifically, point C is right there in space, and now you know exactly what I'm talking about, because we can notate it. Or if we had to just sort of do it out in space, we just put a little dot out there like that, and that's how we can indicate it out in space. Okay? So points are indicated either at intersections, ends of segments, or out in space with a dot. But it's not really a thing because it has no length. It is no dimensional. All right, so then we go to the second definition. A line, so we had a point, now we have a line. A line is breadthless length. Not breathless, like I'm out of breath. Breadthless length. All right, and you can see here that the word breadth and the word width are used interchangeably. Okay, so a line is a solid path that has only length, no width. Catch this. It is one-dimensional. Oh, I see where we're going here. First it was no dimensional, now it's one-dimensional. We'll probably eventually get to two-dimensional and maybe even three-dimensional. Oh, okay. All right. Now, lines can be straight or curved. So these solid paths can be straight or curved. Okay. Mostly in this class, we're going to deal with straight lines, but because we're not going to deal with non-Euclidean geometry. But as you saw the other day, an arc or a circle is a very common curved line that we will be dealing with. Okay. Now, this one's an important one to understand, and this is where it gets a little ticky-tacky. All right. So in modern geometry, the word line, let's put that in quotes because we want to specifically mean this word line, usually refers to then a path that extends infinitely in both directions. And so therefore, when we talk about lines in modern geometry class, we're saying that we draw them with arrowheads on both ends. Now, maybe you remember this from Algebra 1 class when you were, rising and running and rising and running, and then you drew your line on your graph, right? And your teacher probably said, now make sure to put arrows on the ends of that. That's because we want to indicate that rising and running never stops in either direction. It goes on forever and ever, right? So if we're going to draw a modern geometry line, this would be an example of a straight line. We have to make sure to put these arrowheads on there to make it a line. We could also have this. That is possible. We could have a curved line. And again, those arrowheads say this continues in that direction forever and ever. Okay? All right, so that's what we have for our second definition. A line is breadthless or widthless length. It's one-dimensional. All right, so then he goes on and he goes to say, okay, well, if a line ends, because we just talked about how lines don't end, right? He says, but if a line does end, its ends are points. Okay, well, that kind of makes sense, right? Because we just sort of talked about a point as a location in space. So this lets us talk about something called a finite line. Essentially, not infinite, right? Finite is not infinite. And it has ends that are indicated with 2 points. It has ends that are indicated with 2 points. So it could look something like this. We could have this finite experience and put a couple of little dots at the end of it for our points. It could look like we just did in our constructions the other day, where we just have a straight path. But the fact that it stops, that it doesn't go on forever and ever, indicates that there are points there. Okay, so that's important to understand, right? Because if I say, draw me a line, and you draw me this, it's wrong. Right? That has a special name, and we're going to get to that, right? And of course, we can have something that looks like that. That is possible. Sometimes maybe even in algebra class, you've seen something that looks like, let me do this one again just for the fun of it. Ever seen that one? Right? And what does that mean when I put that open circle there? What does it mean, Alexa? It's not equal to that. It's not included in the, so like when we were talking about these on a graph, it would be like the solid point would be included and the hollow point would be not included, but everything in between, right? So these are the ways that we can indicate this as we're looking at some more modern math. Okay, let's get to the last of our definitions for the day. This is the one that's going to be the most important for your homework. So everything sort of leads up to this. All right, so a straight line is a line which lies evenly with the points on itself. I've struggled with how to rephrase that for years, and I just really haven't come up with a good way of rephrasing it. The bottom line is it goes straight through all the, when we use the word straight, it kind of defines what that is, it goes through all the points that sit on itself. All right, so let's just kind of break down the important vocabulary that we need here. So in modern geometry, straight solid paths are broken into 3 types. We have lines, we have segments, and we have rays. These are the 3 groups in which we break solid paths into. Lines are infinite in both directions. Segments are finite in both directions. And rays are finite in one direction and infinite in the other. And again, this only relates to straight paths. And so that's why we're kind of narrowing this down. Now we're bringing this into straight paths. So let's kind of jot these down and give yourself a visual, right? So first we have line, and a diagram for a line would look like that. Okay? And then, of course, we have segment. And that segment would look like this. We could put some points at the end of it, and sometimes you'll see it with points and sometimes you'll see it without points. But again, it's finite in both directions. And then lastly, we have a ray. And a ray is going to look like this. It's like an arrow. It's finite in one direction at one end, and it's infinite at the other. Okay? And so this is how we break this down in terms of these straight line segments in modern geometry. Okay, now, straight paths, lines, segments, and rays, are notated, and I want you to put in quotes here, named, because I'm going to use that language a lot. What's the name of that segment? What's the name of that line? Hey, guys, tell me the name of that ray. Okay? And it's named using exactly 2 points. This is how we name lines, segments, and rays. Not 3 points, not 1 point, not 7 points, 2 points. Exactly 2 points. That's how we name line, segments, and rays. Okay? Now, each type of straight path has its own notation style. And you need to know this. This is super important. Okay? This is akin to writing in your proper language in language class. You got to be able to write correctly in here in our math language. Okay, so give yourself a little squiggle here. All right, and then I want you to write above here diagram and then notation. Diagram or notation. All right, and the notation is the name. Okay, so let's fill in some notes here, and then we'll come back and we'll do some drawing of some pictures. Actually, let's draw the pictures first, and then we'll do that. So here's the first thing we'll do. Let's draw this picture. So we have this diagram here. Let's draw that picture. Let's draw that picture. And then let's draw that picture. So 3 different pictures. Okay. This one. What is it? That's a line. What is this? What is this? Okay, so line, segment, ray. All right, now, line and segment names can be written in either order. Line or segment names can be written in either order in their notation style. So we could name this line right here, line DF, by doing this. Capital D, capital F, and then you put this little symbol above it with 2 arrowheads on it. That is how you write the name in geometry notation, line DF. Or we could call it line FD. Notice I used capital letters because we're talking about points. We're basically saying the straight path that passes through points F and D and extends infinitely in both directions. That's what this reads to somebody who understands geometry. Make sense? This is the straight path that passes through points D and F and extends infinitely in both directions. All right, now, same thing with the segment. We could say this is segment XY. This time it becomes the 2 end points of the line. Okay, we can, if there was another point in the middle, we could use that other point as well. But when we draw our notation, it's just this at the top. Notice no arrowheads because it's finite in both directions. And we don't put points on it. We just leave it a straight line. Again, we could say that as YX. Segment YX. This is the straight path that begins and ends at Y and X. So lines and segments, the names can be written in either order. However, ray names must be written with the finite end listed first. Must be written with the finite end listed first. So let's talk about that. So this figure here is named ray QP, and we put a ray symbol at the top. Now, a couple things that you need to know. I specifically drew this going this way for a reason, because I want to emphasize the point that it doesn't matter whichever way on the paper my ray is going, this always goes to the right. It never goes to the left. Always goes to the right. And the reason why it does that is because what we're saying is the finite point of our ray is Q. And then it passes through P infinitely forever. That's how you read that. Okay, so let's write this And then let's put a big no-no circle through that. Because that's a no-no. Because P is not our finite plane. Okay? P is on the ray, and it starts at Q and extends through P. So we need to make sure to write that. So important when you're writing your names. Good? Everybody got it? That's going to be really important because you're going to have one homework assignment tonight. It's not going to take you very long to do it all. It's going to be one IXL, and it's going to be naming line segments and rays. And so this is a big part of your assignment that's going to help you figure that out, okay? Now, we got one more thing to talk about real quick, and then we're done for the day. All right, so points that sit on the same straight path are called collinear points. That actually kind of makes sense. Collinear, with line. That's what it means, literally translated, okay? And points not on the same path are called non-collinear points. Like nothing fancy about that. Collinear, with line. Non-collinear, not on the same line. So I want to do a little diagram real quick. Do a squiggle here. And then over on the right, let's do a line like this. And then let's do another line like this. I'm going to put a point there. I'm going to call that A. I'm going to point there. I'm going to call that D. And I'm going to put a point there, and I'm going to call that B. Like that. Okay, so based on that last set that we filled in there, let's put a little bullet point here. What we're going to say is that points A and B are collinear. Points A and B are collinear because they sit on the same straight path. Again, we're narrowing our focus in this fourth definition to straight paths. Well, actually, for that matter, so are A and D. They are also collinear because they sit on the same straight path. But according to this picture, points D and B are non-collinear. Right, points D and B are non-collinear. But you'll notice I said according to this picture, right? Because really, if I just put these points out there and I said, are B and D collinear? Well, according to our first postulate, we would say, well, yeah, they actually are collinear because I can actually draw a straight line through any 2 points. See what I mean? So in theory, any 2 points are collinear, but sometimes we'll represent that in a picture because I'll ask you a question like, name some collinear points. And if I put it here, I don't want you to tell me, well, D and B are collinear because in theory, Mr. Farkas, I can draw a line through all of them. I want you to pick the points that are in the visual image and tell me which ones sit on the same straight path. Get it? Okay, all right. Okay, so that's all I got for you. Thank you for persevering through a long notes day. Again, that'll probably be the longest notes day that we have all year long. So good for you. All right, and then you have your IXL homework. It's going to be LB1. I'll post it on Google Classroom for you, but it's going to be level L, section B, first one. It's to 100, but it really shouldn't take you that hard. It's not that hard to do, especially if you get this idea of naming our straight paths, line segments, and rays.